Hi everyone. I got some questions today about this assignment, Worksheet 3.5, and so I thought I would just put together a quick video to run through a couple of the problems from this assignment to maybe get you pointed in the right direction, to hold you over until I see you in class again. So I'm just going to pick a couple of them that I think have the tricky parts to them, and we'll go through them together, and you are welcome to fill these in on your homework assignment, as you're going. So I'm going to start here with number 2 because I think this 2 sitting out in front here is one of the things that's causing our issues. This 2, we know it doesn't belong to x because if it did belong to x, it would be inside the parentheses here, okay? Because it's not, I know that 2 actually belongs over here with the y, all right? And it just got moved over for the purpose of getting the y by itself. So I'm going to put it back where it belongs, and I'm going to do that by dividing because this is multiplication right here. This is 2 being multiplied by that quantity, so I'm going to divide both sides by 2. That gets rid of that. And so now I can think of my equation as y over 2 equals x over 4 to the power of 3. Okay, so now when I go to fill this information out, first of all, parent function. For the parent function, get rid of all of your numbers that would indicate transformation. So that's the 2 and the 4. And so if you look, I'm left with just y equals x cubed as my parent function. Remember, your rule is going to be the opposite of what you see happening in the equation. So in my rule, I'm going to say that x is being multiplied by 4, and I'm going to say that y is being multiplied by 2. So when I plug in the 0.11 here and here, that's really just going to leave me with 4 and 2. Okay, so let's talk about what's happening here. Both of these are going to be stretches because multiplying by 4 and multiplying by 2 are both operations that are going to make a value bigger, okay? So really what we have going on here is a horizontal stretch by a factor of 4 and a vertical stretch by a factor of 2. Okay, and this is going to be kind of a difficult one to think about in terms of drawing the graph because these two movements are kind of working against each other. When we horizontally stretch something, it makes the graph kind of big and wide. But when we do a vertical stretch, it makes it tall and skinny. So these two things are kind of pulling in opposite directions. The fact that the horizontal stretch has a larger magnitude to it means that it's going to win out eventually. So what we want to do is a cubic function that's just slightly stretched horizontally. So let me do this. Let me sketch kind of what I would consider to be the parent function here. Okay, so this is what we would say a cubic function typically looks like. And so the horizontally stretched one is going to look something more like that. It's going to be pulled out to the sides more. And again, it would be even wider than this, except that vertical stretch is kind of counteracting the movement there. Let's take a look. I know that I want you to do these without looking at these on a calculator, but let's take a look a quick second. Parent function y equals x cubed. Okay, this is what the original graph should look like, and you should be familiar with that picture. So when I graph my new function that I have typed in here, you're going to notice that it's kind of pulled out to the sides, right? It's wider than the original cubic function. And again, I'm not so worried about you understanding or knowing how much wider to make it, as long as I can see that you knew it was going to get wider. Now, this 2 that's sitting here, that's the value that would have come from the y, and that's what's forcing a vertical stretch on these coordinates. And like I said, that vertical stretch is kind of counteracting the horizontal stretch. If I take that 2 off of there, notice the graph gets even wider. Okay, so by doing a vertical stretch, what I'm really doing is pulling that stretched graph upward. Okay, and it's making it look skinnier than it would have been with just a horizontal stretch of 4. So in a situation like that where they're kind of working against each other, you just take a look at which one of them is kind of stronger. Just to help you visualize, if I get rid of that 4, whoops, I guess it won't let me get rid of just the 4. There we go. You can see that now that blue graph is quite a bit skinnier. So the vertical stretch is making it skinnier. When I put the horizontal stretch in there, it makes it wider because it's stronger. Okay? All right, hopefully that was helpful. Let's go back and try another one here. All right, let's take a look at number 4, because there is some weirdness going on with number 4. So that 5 up on the top there, again, we know it doesn't belong to x because it's not down here with the x. It's not in parentheses with the x. This one's a little weird to think about being with the y, though, and I'm looking to see if there's another one. So take a look here at number 3. 4 times 1x, 1 over x. If I had just asked you to simplify that, you could have written this as 4 over x. Okay, they just wrote the 4 down in front instead of putting it into the fraction. So here we have to kind of undo that. Here we can think of this as 5 times 1 over negative x squared. Okay, we can pull that 5 down in front. And then, of course, we know that that 5 actually belongs to the y. So this would really be like y divided by 5 now. So my parent function, if I get rid of my transformations, which is really the 5 and the negative sign, I'm looking at 1 over x squared. Okay. For my rule, if I think about what's happening to the x, well, x is negative, right? So I'm going to say negative x. And then the y is being divided by 5, so that's going to be a 5 times y here. As far as this coordinate goes, that's going to be a negative 1 and then 5 times 1. So that coordinate would go to negative 1, 5. By the way, this is something that was throwing some people off on the last worksheet we did. This coordinate doesn't actually help you draw your graph really at all. This is a coordinate that's just showing that, this was on your original graph of 1 over x squared, and that point will move to this spot. But I usually graph based on where the origin is because that's a more distinguished landmark kind of on the graph, so I would not worry about this point as far as your graph goes. Okay, so this negative on your x, that's going to be a horizontal reflection, otherwise known as a flip over the y-axis. And 5 times y is going to be a vertical stretch. Okay, by a factor of 5. So my parent function here, 1 over x squared, looks like this. Okay, a vertical stretch of one of these is going to kind of pull this center away just a little bit. It's just going to make it a little bit more like that. Okay, so it's just going to get pulled upward just a little bit. The other thing I wanted to point out, notice I didn't do anything with that negative x, right? All I talked about was the vertical stretch. A flip over the y-axis, or a horizontal flip, this thing is symmetric over the y-axis. So if I flipped it, this side technically goes over here, and this side technically goes over here. That's kind of what this is saying, is the point 1, 1 would have been on the original graph. When I flip it, it's going to end up at negative 1, 5. So it's going to end up somewhere over here. So as far as the correspondence goes, all of these points ended up on this side, all of these points ended up on this side, but the graph itself doesn't look any different. When you do a flip on something symmetric, it just stays in the same place. Okay, let me pick one more here. Let's look at number 6. So number 6 down here, that 1/5, just like before, actually belongs with the y. To move it over to where the y is, I would multiply by 5 on each side, because 5 and 1/5 will cancel each other out. So I'm really looking at this. 5y equals square root of 3x. Parent function here is the square root function. For my rule, I'm going to say x divided by 3 and y divided by 5. This is another one where they're kind of working in opposite directions of each other. The point 1, 1 would turn into 1/3, 1/5. If you did those as decimals, that's fine. I'm really just plugging in 1 here and here. These would both be shrinks. So this is a horizontal shrink. By a factor of 3, and a vertical shrink by a factor of 5. So the square root function typically looks like this, okay? Kind of a sideways half parabola. A horizontal shrink in this case is going to push this inward, which will actually make it kind of bubble upward. Like it's going to make it look taller because we're squishing everything inward like this. But a vertical shrink is going to shove that back down. So again, it's a question of which one of those things is going to win. If one thing is pushing this way and the other thing is pushing this way, I see that my vertical shrink is stronger. There's a stronger magnitude. So what's really going to happen here is this thing's going to end up looking kind of squished. Now, not as squished as it would have been if I was only doing the vertical shrink. If I was only doing a vertical shrink, it would be pushed way down. But because I did the horizontal shrink too, that kind of counteracted it. That might be another one that would be good for us to look at here. So let's look at square root of x. There's my original. Okay. And then my new function was 1/5. Nope, that's a 2. 1/5 square root of 3x. Okay, so you can see it's a flattened version of what I had before, and probably, I mean, my graph that I drew was teeny tiny, so you didn't see as much of a difference. But so the 1/5 is the thing that's making this graph get shoved downward, but the 3x is making it push inward. So first, let's just look at it with just the 3x so you can get an idea of what that would look like. Okay, you can see with just the 3x, with the horizontal shrink, it actually makes it look taller, because what we're doing is we're taking all of these points and pulling them inward. So like this point here ends up, whoops, it's not gonna let me do that, but this point here is gonna end up over here. Okay, this point here is gonna end up here, and so on. So all of these points are being pulled inward, which is gonna make the curve look taller. If I do just the vertical shrink, all of these points are getting pulled downwards. So these all get pulled down by that factor of 5. Okay. When I put them in there together, they're kind of pulling against each other, but because the 5 is stronger, the 5 wins. So hopefully that helps a little bit. I know these aren't as clear cut as the translation ones are, but you should be able to get at least a rough sketch down for most of these. I'm just looking to see if there's any others that I feel like are going to be extra tricky. I don't think so. I think you can handle the rest of these. Yeah, you should be okay. So we will follow up on this when I'm back in class with you. I'm not going to make you take a quiz or anything on this until we make sure we have plenty of time to talk about it. So just do the best that you can, and we'll talk about it when I see you again. All right, hope you guys have a great day.